Hey, everybody. Just wanted to walk y'all through question 5 from section 1.2 from the first homework. So let's go through this slide by slide, or sorry, part by part. So first question asks, what is the domain of this function? So 1 second. Right. So when we're talking about the domain of a function, we're talking about what are the possible values of the input variable, or what are the possible values of x that I can use for this function. A lot of times the more direct way to answer that question is to think about the things that are going to cause your function to be undefined. So what values of x are going to cause your function to be undefined? One of the big things to look for is division by 0, and that's the situation we have to worry about here. So since we want to avoid dividing by 0, I want to see what is going to cause the denominator to be equal to 0. So I can set up this equation, x squared minus 4 equals 0, or x squared equals 4. The two values of x are going to give me x squared equals 4 are going to be x equals 2 and x equals -2. So basically the domain is going to contain all the real numbers except for these two. So lots of ways to express this. I don't really have any preference for however you want to say it, but there's one way to say it. If you like the interval notation, this also works. So from -infinity to -2, from -2 to 2, and then from 2 to infinity. All of those are open intervals, so I don't include any of the endpoints. But yeah, there are several ways to give the domain of this function. All right, moving on to part B. I want to use a sequence of values of x near a equals 2. So what we're really trying to do here is build up to what this limit is. As x approaches 2, or as x gets very, very close to 2, what does the function do? So there are a couple ways to do this. We're being asked to use a sequence of values near a equals 2. So let's set up a couple of tables here. So x and f of x. I'm going to do one table here to approach from below. So let's say x equals 1, x equals 1.5, x equals 1.9, x equals 1.99. And then let's also do a table that kind of does the mirror image of that. So I want to look at values from above 2. So let's go x equals 3, x equals 2.5, x equals 2.1, x equals 2.01. So from there, if I plug in some values, what do I get? So I think x equals 1, I can probably do that without getting a calculator out. So 16 minus 1, 15 over -3. I believe that's -5. All right, so for my table on the left here are the values I have: -6.25, -7.61, and -7.9601. So if I'm evaluating this limit from below, it looks like we're approaching a value of -8. So let's see if I get the same values on the other side here. So let me change my Desmos work. What's f of 3, f of 2.5, f of 2.1, and f of 2.01. So the values I get here are -13, -10.25, -8.41, and -8.0401. So I believe, and we're not saying this absolutely yet, but I think based on what I'm seeing, this limit as x approaches 2 looks to be -8. So um, again, I could use more values to get even closer to x equals 2. Um, um, and we'd probably get even closer. But for now, I'm going to go ahead and say that, all right, my claim is that the limit is -8. One thing I do want to point out, actually, we'll go ahead and wait for the next slide because I'm pretty sure that's the next question. Okay, so it's not, but I know that part's coming up soon. So let me go ahead and go back to my slideshow. All right, we want to use algebra to simplify this expression. So how can we do that? So lots of ways to simplify these things. Let's try. I noticed that I have both in the numerator and denominator, I have different perfect squares. So one thing I want to do here, and I'm going to be very careful, I do not want to use an equal sign this whole way through, and I think I'll explain more about why that is in a second. But how do we factor perfect squares? As a reminder, I'll come do this scratch work off to the side. A squared minus b squared is equal to this quantity a plus b times a minus b. So that's what I'm kind of relying on here. I know that 16 is 4 squared, so, and x to the fourth is the same as x squared squared. So I can factor this like this, 4 plus x squared times 4 minus x squared. I could do the same thing to the denominator, but I'm going to hold off on that for now. Because one thing we can notice is that this factor on the right in the numerator here is basically the exact opposite. So one more thing I'm going to do here is this. I'm going to factor out a negative sign from that first factor or that second factor, and I get x squared minus 4. Now, what this looks like is this. I can cancel out the x squared minus 4 in the numerator and denominator. But what I don't want to say is this, and I'm going to write it down just long enough to point out what I'm saying is not equal. So the function of x I'm giving to you is this, 16 minus x to the fourth over x squared minus 4. What happens if I cancel this? If I cancel this, I'm going to have negative 4 plus x squared, except I'm going to very quickly remove that equal sign. So why can I not say these things are equal? Here's really the only reason I can't. So we said in part A that x cannot equal 2. The value of 2 is not included in the domain of the function f. Because if we try to put in 2 for x, what did we get? We're going to get basically 0 over 0, which is undefined. But if I plug in 2 to this expression, that's totally fine. So we cannot say that the function f is equal to this, but what we can say is this. The limit as x approaches 2 of f of x is equal to the limit as x approaches 2 of this new simplified expression, which is negative 4 minus x squared. So even though these functions are not equal, they're equal almost everywhere. They agree everywhere except for this one point, but their limits do agree everywhere. So now I can evaluate this limit directly, basically just by substituting. This limit here is equal to negative 4 minus 2 squared, which is negative 8, which is, what we claimed in our last part here. So moving on, and I kind of talked about this at length in part C, but true or false, f of 2 equals negative 8. The answer to that is false. So just to reiterate, why is that false? I just said the limit was negative 8. So why can I not say this function is equal to negative 8 when x equals 2? Well, let's try it. If f of 2 was really negative 8, then I really could just make the substitution. F of 2 equals 16 minus 2 to the fourth over 2 squared minus 4, which comes out to be 0 over 0, which is undefined. So not only does f of 2 not equal negative 8, it doesn't equal anything. It's not well defined. So this is enough to prove to me that this is false. Moving on to part E. Again, I think I talked about this so the expression on the left-hand side of the equal sign is the function. It's what this function is defined as. And this expression is the right is something we got when we simplified. We did a little factoring, did some canceling. But are these two things equal to each other? They are not. This is false. And the reason for that is this. So we already said that f of 2 is undefined. But what about, are you going to erase? No, you're not. But what if we plug into this other thing? So -4 minus 2 squared equals -4 minus 4, which is -8. And that's enough to say that these two things are not equal to each other. I found a single value of x where they don't agree. And that's enough. And really, this is the only value of x where they don't agree. You can pick your favorite value of x if you want, but let's just do f of 0. What is f of 0? 16 minus 0 to the 4th over 0 squared minus 4. That comes out to be 16 over -4, which is -4. Is that also going to work when I plug in 0 to the other expression? It absolutely does. So that really truly is the, actually, sorry, that really is the only x value where this is going to disagree, but all you need is 1. So that one disagreement is enough to give you an answer of false here. And final question, I want to construct an accurate labeled graph of this function on a very tight interval. So let's start here. Let's draw out my coordinate system. And I really only care about what's happening. So let's make pretty big hash marks here, or wide hash marks. 1, 2, 3. And then I don't really only care what's happening between these two dashed vertical lines. Okay. But here's what I do know. I know that when x equals 2, most of what we've done in this problem is to think about what happens at and around x equals 2. So what do we know from previous work? We know that the limit as x approaches 2 of f of x equals -8. We also know that f of 2 doesn't exist. And that's one of the key things to think about or to keep in mind about limits, is that the limit that your function has as it gets close to a point and the value your function has at that point don't necessarily have anything to do with each other. And this is one of those times. So let's talk about this limit. So I know that the limit is -8. So 1, 2, 3, 4, 5, 6, 7, 8. I know that at this value, and lots of our work have shown this, but we know that as we approach from the left and the right, we get closer and closer and closer to -8. So let's actually go back a few slides and look at our table. One thing I'm going to use here is f of 1 equals -5 and f of 3 equals -13. So it's probably the easiest things to graph right now. So 1, 2, 3, 4, 5. Try drawing. Here we go. 1, 2, 3, 4, 5. And then I need a few more hash marks. 9, 10, 11, 12, 13. And f of 3 is -13. But what else do I know? I also know that the limit at 2 exists even though the function is not defined at x equals 2. But what I know is this. Basically, you can think of that, what happens to this function at x equals 2, there being a hole there. There's like a removable discontinuity. But I know the limit exists. So I know that as I approach from above and below, or from the left and the right, whichever way you want to look at it, the curve on either side approaches this point right here, which I'll now label as this point right here, which is to -8. So limit exists there, but the function is not valued there. And again, just to reiterate, the limit of a function, so some of the kind of key words you might think here is this: the limit is what happens as I approach a point or when I get near a point. The value of a function is what happens when I am at that point. And what happens near the point and what happens at the point don't necessarily have to have anything to do with each other. And this is one of those cases where, I can get as close as I want to x equals 2, and I will get closer and closer and closer to a y value of -8. But when I actually allow myself to achieve of x value of 2, the function is not even defined there. So again, it's probably going to feel counterintuitive for a while because in a lot of ways it's subtle and it's tricky. But yeah, limits and the way a function is defined might be different. In fact, they don't even have to both exist like they do in this case. So hopefully that makes sense. And let me know if you have any questions.